Hi there, in this video I thought it would be fun to build one of these transistor testers, of which there are many variants available on eBay and similar places. Usually they are ready made as an assembled PCB and sometimes even in an enclosure, but where's the challenge in that? So I decided to order this as a raw kit instead. It arrived in a bag and this is what you get. A bunch of resistors, a PCB which has the LCD screen stuck on it to protect it from scratches and cracks during transport, which is a rather good idea. A test socket, a rotary encoder, and lots of small parts. Oh, and of course the brain in form of an ATMega 328P microcontroller and a 28-pin socket for it. My kit came directly from Shanghai by the eBay seller Dragon, who sells several variants, including ready-built versions and enclosures. Just shy of £15 or US$20, it took about 3 weeks to arrive in the UK. Several layers of intensely chemical-smelling, strangely soft plastic film wrap the PCB and LCD sandwich. I recommend to remove and discard this as soon as possible because the vapors that stuff emits can't be very healthy to breathe in. The PCB has already some SMD components on it, so only through-hole soldering skills are required. The 3 SMD components are a beefy transient voltage suppressor diode P6KE, an array of ESD protection diodes SVR5-04 and a 100 nanofarad capacitor. Together they prevent bad things on the 3 test inputs from killing the processor, but of course they are not infallible. You can still kill it, especially if you connect large and fully charged capacitors, which will likely wipe out both the protection and the ATMega, so some care is still good practice. Yet this here is much better than no protection at all, and it's nice that it's already on board. The LCD is a color type 160 by 128 pixels using the ST7735 controller. This display is using a serial interface needing only 4 inputs, which makes it relatively slow but frees ports for additional functions on the processor. The display runs on 3.3 volts, which is why it has its own regulator and a level converter to the 5 volt signals from the microcontroller. All that is needed is to solder a row of pin headers into this board. Oh, and in case you wonder, there's zero documentation coming with this kit. Instead, the idea is you follow the silkscreen print on the PCB to identify the right component from the pile you received and put it into the PCB in the right place. I would well imagine that this may cause some issues for beginners. I recommend this site, which is by the guys who developed this type of testers in the first place, because all the devices you see out there are essentially clones. I leave a link in the description. However, this is no beginner's guide either, and because there are so many variants, it is quite complex, compounded by your kit, hardware and software being likely many versions behind this site, so neither circuits nor use instructions are fully applicable. What I did pick up from the documentation on that site is that the accuracy of the 3x470K and 3x680 ohm resistors is quite important for the performance. They recommend using 0.1% tolerance resistors. 0.1% for these values is very hard to get. Let's see what we've got in this kit. Well, that one doesn't meet that, almost 0.7% out. Oh dear, 1.4% out, and back to 0.7%. Maybe the 680 ohm ones are better? Almost 0.8% out. Amazingly, exactly the same resistance as before, but still 0.8% out, and slightly better at 0.7%. Except for the first one, they are within 1%, which isn't bad. Certainly usable, but if you have a few more relative inexpensive 1% resistors and a way of measuring them to at least that accuracy, it's possible to do better. Like here, I found a few 680 ohms and 470K 1% V-shape branded resistors and simply measured them one by one until I found 3 that are within 0.1%. Using the histogram of these two measurement series, I picked these three 470k resistors and these three 680 ohm resistors. All of these are well within 0.05% tolerance, slightly over the top, but why not? When populating a through-hole PCB, starting with the lowest component, like in this case resistors, makes sense because it prevents them from falling out when soldering. Those critical 680 ohms and 470k resistors go here, right next to the ATMega. Well, my 470k resistors were 1/8 of a watt, I believe, and they went in easy, but my own 680 ohm resistors are slightly too large to fit lying flat into very tight footprints. They use the same for all resistors, and even the kit's resistors barely fit into it. This is annoying because they actually have the space for larger footprints. In any case, because the 680 ohm won't fit lying flat, they will have to wait until all the other resistors and some of the other lower components are in. I recommend not trying your luck with color codes, which on these resistors I find always hard to decode reliably. Instead, use a multimeter. Even a budget one will do nicely to make sure you really got a 2.2K in your hand. For resistors of the same value that come in bands, I then write the resistance on the band to avoid confusion and always finish one band before moving to the next value. I randomly grabbed a band with two 3.3K from the pile. Then looking where they should go on the PCB. Make sure not to confuse it with the 33K next to it. Okay, the two 3.3Ks are in. Now we have 6 times 10K to fit. 3 go down here, 2 go up there, and 1 should go over there. With the 10K resistors in, I grab the band with two 1K resistors next. They go down there parallel to each other. And there they are, onwards to 27K. Before you go to the assortments of single resistors like I did, I would like to briefly interrupt the happy soldering. Because much later I discovered a section in the documentation about measurements of Zener voltages above 4 volts. Now I knew that my kit did not have the extension to generate the necessary high voltages on board, so I skipped over that. But later I discovered that they kind of half implemented it for the purpose of measuring external voltages up to 50 volts, and maybe with an upgraded firmware that feature can be used to measure Zener diodes as well if you provide the voltage yourself, something to investigate later. The point of the interruption is that this part of the Zener extension circuit, apart from that capacitor, is actually included in the kit. There is the place for these two resistors, 180K and 20K. They form a divide by 10 voltage divider, so it pays to check the accuracy of these resistors. I did not do that when I built mine, but I got lucky. In my kit the 20K is well within 0.1% and the 180K is just below 0.4%. To continue with the build, now all resistors apart from my slightly too large 680 ohm resistors are on board. Time to move on to the next higher component, which is the IC socket. On these, I usually solder just one pin on each side to check and if necessary correct the alignment. Seems okay, so I can solder the rest of the pins. That done, and after making sure no pin got forgotten, the next component, height-wise, is the 8 MHz crystal, which sits right next to the microcontroller's input for the clock or crystal connection. There's quite a number of very similar looking capacitors in this kit, and you might want to try measuring them to make sure which one you've got. Be aware that it isn't easy, especially for low capacitances. Many meters like my Brymans may not even show them, or if they do, like the AN8008, it shows 23 picofarad just from my measuring leads. The AN8008 does not have a rel mode, so if I connect a cap, we have to mentally subtract 23 picofarad from 50 picofarad, meaning this capacitor measures about 27 picofarads. It is in fact a 22 picofarad, but the accuracy of the AN8008 is certainly good enough to get a ballpark figure, because the values in this kit are quite far apart. The next closest is 1 nanofarad, so you'll definitely be able to distinguish these two. The largest cap of this type in this kit is 100 nanofarad, and again the meter will tell you easily if you have got one of them. These three have 22, 1000 and 100,000 picofarads, an enormous difference in capacitance, but from the outside they are nearly identical and easy to mix up. Lacking a meter, you can also sort them using the number that's printed on them. In the top we have 5 caps marked as 104, which is a 10 followed by 4 zeros, or 100,000 picofarad or 100 nanofarad. Below that a 103, which is 10 followed by 3 zeros, meaning 10,000 picofarad or 10 nanofarad. Then we have a 102, which, if you follow the same scheme, translates to 1000 picofarad or 1 nanofarad. And finally we have a 220, which means 22 and 0 zeros or 22 picofarad. You may have to get your head around that one. A 220 is a much smaller capacitor than a 102. The 22 picofarads are used for the crystal oscillator, and I decided to replace one of them with a green trimmer cap of 30 picofarads. It is right next to the crystal. I did this to be able to tune the clock closer to 8 MHz, but later I replaced this with a yellow 40 picofarad trimmer because 30 picofarad wasn't enough. In hindsight, you may want to stick with the fixed caps that come with a kit, because adjusting the clock is not easy and the frequency wanders quite a bit in the first 5 minutes or so of operation, which is often all the time you use it for. Continuing with the build, we have got 5 similar looking transistors, but in fact only the 3 on the left are transistors. One general purpose PNP S9012 and 2 general purpose NPN S9014. Second to the right we have a TL431A, which is a programmable reference which is set to 2.5 volts. The A means it's a 1% tolerance part. Not as good as B, which is 0.5%, but still better than if there wasn't a letter at all, which means 2%. On the most right is a 7550 low power, low dropout 5 volt regulator. All transistors and the 2 that look like transistors are in. When soldering these in, make sure you don't get them stick out too much, because the LCD will be on top and there's about 10 mm clearance between the 2 boards. And finally it's time to add the 680 ohm resistors. Here they are. They are lifted on one side to be able to fit them. I did not want to mount them properly standing because of the limited clearance of the LCD above. Next are the relatively tall components like these 2 10 microfarad electrolytic capacitors. I was skeptical on the brand Hua Hong, but I tested these with my LCR meter and they are surprisingly decent in quality and ESR. The electrolytic capacitors are in, and I also added the connector for the display PCB. To solder the row of pin headers into the LCD, I recommend plugging them into the socket on the main PCB and then insert the LCD into them, while resting it on the 2 standoffs on the other side. That way, the correct alignment of the LCD and pin headers is practically guaranteed when doing the soldering. I also added the battery cable and the rotary encoder because I thought I should be able to power the unit on at this stage, despite that there are still so many empty spaces on the PCB. You see, I'm not too excited about a couple of things in the design of this kit. As a start, there are these cheap screw terminals for measuring frequency voltage and frequency generator output. I'd much prefer to plug a test lead in. Next, access to the ZIF socket isn't great because of the raised LCD blocking one entire side and the battery is just hanging in the breeze. My plan was to put this whole thing in an enclosure of sorts, replace the horrible screw terminals with 4mm sockets for test leads, raise the LED and the ZIF socket onto the level of the LCD for easier access, and last not least secure the battery. Hence I left all these things out when assembling the PCB. After supplying 9 volts to the battery terminals, nothing happened. And it took me a while to remember that the barrel plug connector has a switch built in that only connects the battery to the circuit if no plug is inserted. Without a barrel plug connector, the battery isn't actually connected and I had to bypass it. Yeah, 5 volts, so that part is working. The second thing to check at this stage is the reference voltage source at pin 27, which is close to 2.5 volts as it should. For convenience, I soldered the barrel plug connector in so the battery is actually connected while no plug is inserted. I put the ATMega 328P into the socket and plugged the LCD in. The screen comes to life and stuff appears on the screen. So far so good. Yet still, this doesn't seem to work as it should. For one, everything stops in the moment I let go of the rotary encoder. Here's the schematic of the official transistor tester. Unfortunately, the only complete schematic is for the most basic version. The one I got resembles this in principle but has a number of differences. In part, this is because there are extensions like the rotary encoder and input protection which follow the recommendation in the official tester but are not shown in the basic circuit diagram here. From what you see, my tester uses a completely different LCD based on the ST7735 requiring far fewer connections. The voltage reference is different. It has not got an in-circuit programming connector and instead provides a socket for the microcontroller. And for external power, my kit uses a barrel plug and switches the negative battery lead, while this schematic here uses a socket for a tip sleeve connector and switches the positive battery connection. Also, this polarity protection diode is missing in my kit. I recommend putting the diode back in, for example, wired directly into the battery cable or the cable to the external power supply. It's just good practice. It is so easy to accidentally touch the 9V battery terminals with the connecting clip the wrong way around. It doesn't clip in, of course, but the brief wrong polarity could already cause damage. A simple 1N4148 diode works as the power draw at 9V is only around 25 mA. With that out of the way, let's examine this 3-transistor circuit briefly. It turns out that the 5V voltage regulator is normally not connected to the battery or external supply voltage because T3 is not conducting. Pressing the test button activates T3 via T2 and now we have VCC. T1 and the LED provide an alternative way to T2 and the test button to keep T3 activated and the power flowing even when the test button is released. The idea is that the microcontroller software can control T1 using this data line and therefore can after some time turn its own power off. This circuit implements a neat way for near zero battery current draw when the tester is in the off state without needing a physical power switch. In case you're wondering what T2 actually does apart from allowing the initial start, its job is to signal additional presses of the test button to the microcontroller using this data line. In summary, in this circuit, the LED is not just a simple indicator. It provides the base current to keep T3 conducting and therefore the regulator supplying VCC and hence the microcontroller running. When the LED turns off, it's not because the power is gone. Instead, it signals that the processor wants the power to be switched off, which T3 will then perform immediately after. Because I skipped soldering the LED into the PCB, the microcontroller can't control its power and T3 turns everything off as soon as the test button is released. With a better understanding of how this tester works, I had to add the LED on the top left. This is much better. One press and it springs to life and keeps running, testing a not soldered in SIF socket. Okay, so yes, there's obviously nothing there that can be tested. And without further interaction, it gives the advice that the tester needs to be calibrated and how to do that. Basically, I need to shorten all 3 test inputs and then disconnect them again when asked. Seeing these instructions, I decided to abandon my original repackaging idea and just soldered everything in that was still missing on the board, SIF socket and the screw terminals. By the way, the link on the display is a bit cheeky since that would require a Subversion version control client, not what most people have installed, and anyway, the repository has since moved. And then it turns itself off. Nice to understand now how it did that. Okay, with everything on board now, I inserted a quickly fashioned 3-legged piece of wire into the SIF socket that shortens the 3 test inputs. Let's do a calibration. So far so good. Now quickly out with a short. some more cryptic stuff. And now this. What is this supposed to mean? Did the calibration fail? Obviously there's more to it than the on-screen messages, and I decided to read through the self-test section in the documentation, which also explains the meaning of the cryptic messages shown earlier. Let's do it again, but this time prepared. It starts with the shortened test inputs, where it measures the resistance of the short to be able to subtract it later for measurements. Obviously this makes more sense for probe wires, not for this tiny piece of wire. Removal of the short as before. I think these are the measured internal resistances of the data ports inside the ATMega. And these are the zero offset capacitances of the 3 test inputs that need to be subtracted from capacitance measurements. This message that confused me earlier simply asks to connect a decent capacitor greater than 100 nanofarad and less than 20 microfarads between pins 1 and 3. I believe some other transistor tester kits come with a spare capacitor for this purpose, but that wasn't the case in this kit, so I have to supply my own 220 nanofarad capacitor. The values shown are some correction factors determined by the program. And that's it. Apparently my tester came with version 1.12k loaded. Since the current documentation is for 1.13k, it's at least one revision behind. My nominal 220 nanofarad test capacitor is still connected, so the tester now switches to measure capacitance and ESR. How does this compare with my LCR meter? Well, the capacity is kind of okay, but the ESR is more than 10 times off. Why is that? ESR depends on a lot of things, mostly temperature and frequency, and the datasheets specify ESR at a certain sine wave frequency. The tester uses a rectangular wave of a few kilohertz, while the LCR meter at the moment uses a clean 1 kHz sine wave. If I change the test frequency to 10 kHz, I get a different ESR, much closer to the one of the tester, but also a slightly different capacity. ESR measured with this tester can't really be compared to LCR meter measurements or with datasheets. But to be fair, the tester documentation explains that, and the methods used are quite ingenious and have been continuously improved over the different versions. It is well worth reading. Also, ESR measurement works better for higher capacitance than 220 nanofarad. What else can this kit measure? We have transistor, of course, which is the default function and would be better called auto test because it tries to guess whatever you plugged in and measures it, be it semiconductors, resistors, capacitors or inductors. It can measure frequency and has some sort of frequency generator, a 10-bit pulse width modulation output, a special in-circuit capacity and ESR measurement, a resistance and inductance mode, the 1 and 2 by the way refer to which test inputs are used, a capacitance mode without ESR, testing a DS18B20 temperature sensor, entering correction factors for measuring large caps, infrared decoder test, infrared encoder test, testing of DHT11 temperature and humidity sensors. Self-test is the calibration program, measuring voltages. Font color changes the color of text and symbols. Back color changes the color of the background. Show data shows the calibration data and the symbol icons in use. Well, and you can switch the unit off. I have not talked about how to adjust the clock frequency, which is rather tricky and not too stable, so I'm not recommending adding the trimmer. Well, if you want to do it, you need of course a good frequency counter, and to reach the trimmer, the LCD needs to be off. Initially I thought that's not a problem. I just connect the counter and scope to one of the crystal leads and adjust until I see 8 MHz, but it turns out that probing so directly changes the frequency of the oscillator. A better way is to temporarily extend the connection between the LCD and board so you can select a frequency from the frequency generator and then adjust the trimmer to get the output as accurate as possible. Before looking a bit closer at some of the functions you saw in the menu, I want to add some information about extensions in the basic schematic discussed earlier. I already mentioned the external voltage input. The kit skips the 10 nanofarad capacitor. The circuit is actually meant to test Zener diodes, and the full extension adds a boost DC to DC converter to generate the 50 volts on board. That part is completely missing, so the voltage has to be applied externally, and all the firmware offers is measuring it. No Zener test. There's also no protection of any kind. Wrong polarity or overvoltage will likely kill the microcontroller. Other extensions are, of course, the rotary encoder, which is following this diagram, and the frequency input kind of follows the recommended schematic, but the kit removed the 10K trim pot to adjust sensitivity, and it's also lacking the 470 ohm resistor. Frequency output is simply a connection to test point 2 without any buffering. In total, the extra connectivity of the kit looks like this. Frequency input up here, output down there, and voltage input next to it, all done by dual screw terminals where the second terminal in each case is the ground. The component test uses the SIFT socket, which provides TP1, 2 and 3, and for SMDs you can use the patch here. I'm actually quite happy that TP2 is also available on the screw terminal for frequency out, which allows easy connection to a test lead, but sadly TP1 and TP3, which are far more frequently used, lack this convenience. As an example, here I'm running the default auto or transistor test with a rather big MOSFET scavenged from somewhere. The leads are too thick to be stuffed into a SIF socket, and therefore I have to clip in blank cable ends of probes to be able to test it. This works fine, of course, and the tester shows a lot of information including pin outs. But I was getting quite tired of having to clip blank cable ends into the SIF socket because you need to do it a lot, also for testing large capacitors and inductors. Therefore I decided to add a fourth screw terminal for TP1 and TP3 and drilled 2 holes in the unused PCB area up there. The screw terminal is super glued in, of course, because there are no tracks on the other side to solder it in. This is how that looks from underneath. The 2 terminal pins are simply wired to the corresponding SIF socket pins. Oh, and yes, I've decided to remove the battery leads for now, as they only get in the way. And a quick continuity test shows that TP2 is, as expected, on the frequency out terminal, while TP1 is on the left of the new terminal, and TP3 on the right. This allows to connect proper test leads. The extra capacitance is about 13 picofarad, which I could have eliminated by running another calibration, but I decided to skip it for now. I decided to use the so modified tester to check my reference capacitors. These are 1000 picofarad, 1% mica types, and the tester is quite accurate. Moving on to slightly bigger caps, all 5% types, 100 nanofarads, 200 nanofarads, 1 microfarad or 1000 nanofarad. The LCR meter measures this one as 960.3 picofarad. 2 microfarads or 2000 nanofarads. All these match almost exactly the capacitances measured by my LCR meter, an excellent result. Stepping up to bigger caps, these are polarized 20% high quality caps, 10 microfarads, 100 microfarads, 470 microfarads, 1000 microfarads, 2000 microfarads, all very close to the LCR measurements, and it's amazing how fast the tester works. With a multimeter you would have to wait many seconds before a measurement is produced. For something even bigger, I have this contraption of 2 4700 microfarad caps in parallel. Let's see how long that takes. Slightly longer than before, but still lightning fast in comparison to the time needed by an ordinary multimeter. Having a way of connecting test leads now allows convenient measurement of in-circuit capacitors, as on this little amplifier board. It works just fine once you get a proper connection. This is a very useful feature. Let's have a look at inductors. My references all have 10% tolerances, but are all in the microhenry range, which is a problem because the tester's lowest range is millihenry. it selected automatically the RL mode and shows 1.05 millihenry or 1005 microhenry. It shows 0.44 millihenry and nearly at its limits it shows 90 microhenry for 100 microhenry and 10 microhenry for 10 microhenry, but this is really the lowest possible value it can measure. Yes, it does not recognize 1 microhenry as an inductor and shows only the resistance value. Looking around for a bigger inductor, I picked up this transformer and its primary winding for 230 volts. That measures 21.7 Henry and 1094 ohm resistance. Checking with the LCR meter using 1 kHz gets just below 24 Henry. Given the totally different method, I call this close enough. And the DC resistance is 1095.1 ohm. The tester was off by just 1 ohm. On to resistors. These are all 0.1% except for the 100 megohm one, which is 1%. With shortened leads, the tester reports 0.18 ohms. Again, a recalibration would fix that. I ignore it for now. 1 ohm, which is okay. 10 ohm, spot on. 100 ohm, slightly low. Same with 1K, probably because it thinks there's a sizable inductance here that isn't there. 10K is fine. 100K as well. 1 meg ohm shows at 1003 kilo ohms, which is alright. 10 meg ohm, okay. As expected, 100 meg is out of range. The results are certainly usable. The misreading of inductance in some cases could have been avoided if this firmware allowed selecting a dedicated resistance only mode, but it has not been included. Measuring frequency next, and I'm using the function generator in the O1 HTS272S for that. It is set to 100 Hz square wave and the tester shows 100 Hz. How accurate these measurements are depends of course a little on the calibration and drift of the 8 MHz crystal in the tester. In fact, up to the frequency of 25 kHz, the tester first measures the frequency and then measures separately the period, that is the second line, and converts that to frequency, which is the third line. Same method, but now 1000 Hz and no problem here. 25 kHz, this is the highest frequency with period measuring. 26 kHz, and from now on only frequency is measured. 50 kHz now. Half a megahertz, no problems. 1 megahertz. 2 megahertz is still fine. And so is 3 megahertz. But 4 megahertz is too much. Sine or square waveform is no problem, but 3 megahertz is the limit for this tester. After testing measuring frequencies of an external generator, the roles are now reversed. The frequency is generated by the tester and shown on the scope, which also shows frequency on the bottom left. This firmware version does not allow selecting arbitrary frequencies, but there are a lot to pick from anyway. At 100 kHz, we can see the first hint of rounding at the square wave slopes, but the frequencies are accurate to the degree the scope measures them. 1 MHz and the steepness of the slopes have decayed a lot. This is not the scope's fault. It can show 1 MHz square waves that are still more or less square. 2 MHz is the top frequency anyway. The 10-bit PWM mode now, and that offers only 7830 Hz, but you can change the pulse width to your heart's content. The reason for that particular frequency lies within the way the PWM is generated by the microcontroller. It is the clock frequency of 8 MHz divided by 1024, that is 10-bit. When going beyond 100%, it wraps automatically around to 0. And how accurate is that? For that, I'm using my BM869S multimeter to show the duty cycle. Just playing around with different PWM settings, and it turns out the tester is pretty accurate. The last test I want to show is the voltage input. As I explained, this was kind of planned for high, that is higher than 4 volts or so, set diode measurements, but neither the DC to DC voltage generator nor the set diode measurement firmware is implemented in this tester. Instead, we have a simple input to measure voltages, which uses a resistor divider to divide the input voltages by 10 to stay within the ADC range. I used the resistors in the kit and they are reasonably accurate, which you can see on these measurements. I have demonstrated the functions in green. For some, like the temperature or humidity sensors, as well as the IR decoder encoder, I simply did not have a suitable test object. All in all, these are a lot of functions you get for less than £15 or $20, and most work really well. The only problem is that given the measurement method, the ESR values are not directly compatible to data sheets or LCR meters, but relatively they give a good indication of good or bad capacitors. Capacitance itself is measured extremely fast even for very large electrolytic caps. It is debatable how useful some of the tests are, for example how many have a DHT11 and want to test it. The selection of tests included is actually controlled by configuration files when compiling the firmware, and this is what the kit developers have selected. It turns out there are more tests available and also newer firmware versions. I debated if I should show later or different configured firmware versions, but in the end I decided to show this one in detail because it's the version that comes with the kit, and many people will probably never try to change it or lack the necessary tools to reprogram the microcontroller. But not to worry, there will be a part 2 of this video where I show how to change the firmware if you are so inclined, and some of the differences in the way the newer firmware works. So if you have not subscribed already, hit that button and the notification bell so you don't miss the next videos, and maybe consider becoming a Patreon, link in the description. As Patreon you get early access to videos, a blog and other exclusive content. Thanks for watching.